Good evening, Malayla.
Good evening.
Can you hear me okay?
Yes,
How is the focus?
it's good. I can see your screen.
All right, I'm going to start closed captions. It looks like Karen is getting ready to join us. What can I do for you? Would you like to ask a question, Malayla?
Yes, I would like to go over the not last lecture, the one before that one. I've been a bit confused about that one.
Okay, so day 12.
Right.
Let me check the class notes so that I can see the day 12 lecture notes. It was the beginning of proof by cases and the quotient remainder theorem. So are you looking at the class notes?
Yes.
All right. Um, let's go through those class notes together so that I can understand what it is that's confusing you. I'm going to share my screen and we're going to look at those class notes. All right. Can you see those all right?
Yes.
Do you understand what the quotient remainder theorem says?
Mm-hmm.
Okay. So we're okay with the statement of the quotient remainder theorem?
Yes.
Okay, good. And just to reiterate what it does say, it says if we have an integer a and a divisor d, there are unique integers q and r, the quotient and remainder, such that a equals dq plus r, where 0 is less than or equal to r is less than d. And that just says the remainder cannot be negative, and the remainder must be smaller than the divisor d. And we also talked about a mod d and a div d on day 12. Do you understand example 1, where we're applying the quotient remainder theorem to find the q and the r?
Yes.
Great. Do you understand how dividing by d equals 2 splits the integers into two subsets that we call the evens and the odds?
Mm-hmm.
So when a number is even and we divide an even number by 2, what remainder do we get?
Sorry?
When we have an even integer, let's call it a, and we divide a by 2, what remainder do we get when a is even? Okay, let's take a look at our picture here, because it might not be that you quite understand what's going on with this picture. Do you see
No.
this picture of the integers?
Yes.
Well, we've split it in half, and one half of the integers are the even integers, and the other half of the integers are called odd numbers.
Mm-hmm.
To connect the evens and the odds, which we sort of understand, with the idea of dividing by 2 and getting a remainder, we can see that the even numbers give us a remainder of 0 when they are divided by 2, whereas the odd numbers always give us a remainder of 1. For example, in example 1, let's look at part Roman numeral 2. A is 37. No, excuse me. Let's look at Roman numeral 1. A is 99. Now, is 99 even or odd?
Odd.
That's right. And look, when we divide 99 by the divisor d equals 2, we do get a remainder of 1. That's true for any odd integer a. If we divide any odd integer a by 2, we get a remainder of 1. But if we divide an even integer by 2, we get a remainder of 0. That's what it means for an integer to be even or odd. It means we get a remainder, either 0 or 1, when we divide the integer by 2. We get 0 for the remainder if the integer is a is even. We get a remainder of 1 if the integer, which is a, is odd. Does that make sense?
Mm-hmm.
And here, do you understand what was happening at the top of page 2? Shall we look at that?
Yes.
Okay. Do you notice here in my picture? I called the evens by this notation, 2 times z, the integers. And I named the odds 2 times z plus 1. Well, I didn't just make those up. Those are the assigned names for the evens and odds. And page 2 shows us why. If we take the integers, we can write them in what we call roster notation, as I've done here. Do you see how this is the integers?
Mm-hmm.
Good. It turns out we can perform arithmetic operations on entire sets. Here the set is z, the integers. We can multiply the entire set of integers by the number 2 by taking each integer and multiplying it by 2. And that's what's done on the second line. When we multiply -3 times 2, we get -6. When we multiply -2 times 2, we get -4. When we multiply -1 times 2, we get -2. When we multiply 0 by 2, we get 0. 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. So do you see how 2z makes sense as a way to name the evens?
Yes.
We can also perform arithmetic where we just add something to every element of a set. So if we start with 2z and we add 1 to that as a set, it means take each element of 2z and add plus 1. So when we add 1 to -6, what do we get? What is -6 plus 1?
Sorry?
What is -6 plus 1?
-5.
And that's how we get this -5. What is -4 plus 1?
-3.
And we get -3. What's the -2 in 2z plus this 1?
-1.
Do you see now how we are getting the odd numbers when we take the evens and add 1 to each one of them?
Mm-hmm.
And that's why it makes sense to call the odds using this, to name the odds using this notation, 2z plus 1. And then we talked about what happens when we use a divisor bigger than 2. For example, what if we use the divisor d equals 3? Well, the first question to ask yourself is, what are the possible remainders when we're dividing by 3? Well, the remainder, if we go back and look at the QR theorem, it says the remainder can be 0. That's the smallest it can be. And the largest it can be is 1 less than d. It has to be smaller than the divisor d. So when the divisor d is 3, the possible remainders are 0, 1, or 2. Does that make sense?
Yes.
So, in the same spirit that we could name the evens and the odds using notation 2z and 2z plus 1, where 2z is really 2z plus 0, but we never write the plus 0. And 2z plus 1, of course, is exactly what it says. It's 2z plus 1. And those names are based on the remainders, 0 and 1. Those are the two possible remainders when we're dividing by 2. When we're dividing by 3, we can get remainder 0 or 1 or 2. So we can name the integers that are multiples of 3. These are divisible by 3. They leave a remainder of 0 when they're divided by 3 by the name 3z. And the integers that leave a remainder of 1 when they're divided by 3 can be named as a set by the name 3z plus 1. And those integers that leave a remainder of 2 when they're divided by 3 can be named by the name 3z plus 2. And in some sense, we think about these integers that are in these 3 slices of this pie as sort of being glued all together into one big chunk, and we are treating them sort of like a single entity, the 0 group, the 1 group, and the 2 group. Does that make sense?
Mm-hmm.
These groups are called classes. And over here on the left side, we have verified for some of, see these blue numbers that we have written inside the pie pieces, like 0 and 6 are inside the set that we're calling 3z. Well, if we go over here and apply the quotient remainder theorem to a equals 0 and a equals 6, we're dividing by 3, we get a remainder of 0 for both of those. And that's why 0 and 6 belong in 3z. Does that make sense?
Mm-hmm.
1 and -8 and -2 are integers that belong in 3z plus 1. Let's look over here at our arithmetic to see why. 1 is equal to 3 times 0 plus a remainder of 1. -8 is 3 times -3. That's the quotient, -3, plus, again, a remainder of 1. And -2 equals 3 times the quotient -1, but again, plus a remainder of 1. We don't even really care about the quotients that much. We're really interested in the remainder that we get when we divide 1 and -8 and -2 by 3. For all of those, we get a remainder of 1, and that's why they belong in this piece of the pie. Does that make sense?
Mm-hmm.
And then 2 and -7 are a couple of examples of integers that belong in the set 3z plus 2, because when you divide 2 by 3, you get a quotient of 0 and a remainder of 2. When you divide -7 by 3, you get a quotient of -3. But the most important thing is we get a remainder of 2. And that's why 2 and -7 both belong in this group that we call 3z plus 2. So to recap, whatever our divisor is, we can split up the integers into classes based on the remainder that we get when we divide integers by that divisor. When D is 2, we get 2 sets. Those with a remainder that is 0, we call those the evens, and those that give a remainder of 1, we call those the odds. When we divide by 3, we get 3 classes, 3z, 3z plus 1, and 3z plus 2. And in general, if we just think about D as a general number that's bigger than 2, then we get D classes based on the remainders. And of course, the smallest remainder, as always, is 0, then remainder 1, all the way up to the largest integer that's less than the divisor D. And if you think about the way the integers are lined up on the number line, the largest integer that's smaller than D is the one right before, and that's D minus 1. And that's why these classes are called DZ, DZ plus 1. The next one that we didn't write would be DZ plus 2. Keep on going, DZ plus 3, ... And the last class would be DZ plus D minus 1, because D minus 1 is the biggest remainder we can get when we're dividing by D. Does that make sense?
Yes.
So the point is we actually care a lot about the remainders. And there are two functions called a mod d and a div d. And they're defined based on this quotient remainder theorem, which is written again here at the top of page 3 for our reference. D is what we're dividing by, it's our divisor. Q and R are the quotient and remainder. And of course, A is the integer that's getting divided up. So we define A mod D to equal the remainder R that we get when we use the quotient remainder theorem and divide A by D. And A div D is defined to equal Q, the quotient guaranteed by the quotient remainder theorem when we divide A by D. Does that make sense?
Yes.
Mm-hmm.
What we care about most is the remainders. So there's actually a translation. If we are told that A mod D equals R, well, that means that A is equal to D times some quotient Q plus that particular remainder R that is sitting here. It's just shorthand. A mod D equals R is shorthand for saying, hey, when we divide A by D, the remainder we get is R. Now, did you have trouble with example 2? Shall we look at that?
Yes, please.
Okay. The thing to keep in mind is now we really are only thinking about the remainders because the mod function is all about the remainders. So let's read this problem. It says, suppose A mod 6 equals 2 and B mod 6 equals 3. Before we even read the question below, the two questions below, let's think about what it means to say A mod 6 equals 2. Here's our definition. A mod D equals R means that A is equal to DQ plus that remainder R. What's the divisor when we say A mod 6 equals 2? What part is our D?
It would be 2.
All right, let's look at our definition. I'm glad we're discussing this. A mod D equals R.
Oh,
R is the remainder. What's the
okay.
D?
So the D would be 6.
R.
Yeah, D is the divisor. It's what we're dividing A by. So
Okay.
when we say A mod 6 equals 2, A is what's getting divided up. It's our dividend. 6 is the D, the divisor. So we're dividing A by 6. And saying A mod 6 equals 2 means, hey, when we divide A by D equals 6, see, that's where the D is. It's right here. The remainder we get is 2. What does it mean to say B mod 6 equals 3? Does anybody want to try to say that in their own words? What B mod 6 equals 3 means?
I'll try.
Please, Abu, do try.
You divide 6 by B, you get a remainder of 3.
That's close. That's very close. But A is the B. Our A here in our definition is the B here. The D, the divisor, is sitting after the word mod. So do you want to try again?
6 divided by a number will give you a remainder of 3.
Almost. B is being divided by 6. If the 6 was here where the B is, then 6 would be being divided by something. But the first number that is written in A mod D equals R, that first number is what's getting divided up. So here B is being divided by 6, and we're told the remainder is equal to 3. Does that make sense?
Yes.
Yes.
So the remainder is on the right-hand side of the equation. The divisor is in the middle. The divisor D sits in the middle. And the dividend, the number that's getting divided, is first. So you could read A mod 6 equals 2 like this. A divided by 6 gives a remainder of 2. B divided by 6 gives a remainder of 3. Whereas the div function says A, when divided by D, gives a remainder of, gives a quotient of Q, and, B divided by D would give a quotient of something else. All right. Keep in mind that this equation, this if and only if equation to definition translation can help us when we try to work the problem. We're asked to find two things. We're asked to find A plus B mod 6, and we're asked to find AB mod 6. Let's take a look at the work that we can do to set ourselves up to answer both of those questions. Okay? So we are given that A mod 6 equals 2. According to our translation, since A mod 6 is D, equals 2, 2 is the R, that means A is equal to 6 times some quotient, we'll call it Q1, it's an integer, plus a remainder of 2. That's what it means to say A mod 6 equals 2. It says, go ahead, divide A by 6. You'll get some quotient, it's an integer, call it Q1, plus a remainder of 2. And knowing that B mod 6 equals 3 means divide B by 6. You get some quotient, it's an integer, we'll call it Q2, plus a remainder of 3. So we get this equation for A and this equation for B, and Q1 and Q2 are integers. Are you with me? Everybody with me? Malayla, does that make sense?
Yes.
I'm just directly using this translation to rewrite the information A mod 6 equals 2 and B mod 6 equals 3 to get these equations for A and B. The point is 2 and 3 are the remainders, 6 is the divisor in both cases, and these quotients are just integers. We'll never know what they are. They could be any integer, and we'll always get the same answer when we find A plus B mod 6. We'll always get the same answer when we find AB mod 6, as long as the A that we pick gives a remainder of 2 when it's divided by 6. Excuse me. And the B that we pick always gives a remainder of 3 when it's divided by 6. So here we go. We want to find A plus B mod 6. So we look at A plus B. Well, there's our equation. I'm going to make this a little smaller. Well, that's a little too small. Okay. So we have an equation for A. It's 6Q1 plus 2. So we can substitute that in for A. We have an equation for B. B equals 6Q2 plus 3. We substitute that in for B. And then what are we doing? Well, let's look at what the question is. What we wish to find is A plus B mod 6. That's why we're looking at A plus B. But what does A plus B mod 6 really represent? Well, it's the remainder when A plus B is divided by 6. So we want to get A plus B looking like 6 times an integer. And then if we have a legal remainder, that's going to be 0, 1, 2, 3, 4, or 5. If we're dividing by 6, the biggest remainder is 5. The smallest is always 0. But once we get A plus B looking like 6 times an integer plus a legal remainder, then we'll know what our answer is. So let's just add A plus B. The 6q1 plus the 6q2 can come up here together. And plus 2 plus 3 is plus 5. Well, we factor the 6 out of the q1 of the 6q1 and the 6q2, and we get a new integer, q1 plus q2. That's our new quotient, q. And our remainder is 5, because 5 is the right size to be a remainder when we're dividing by 6. So the answer is that a plus b mod 6 is always 5. So we're translating back from having the equation for a plus b to having the mod function a plus b mod 6. The remainder here is what a plus b mod 6 is equal to. Does that make sense?
Yes.
Great. And we do the same game to find AB mod 6 in part 2. Let's remember what we're really trying to find. We're trying to find the remainder when AB is divided by 6. And that remainder has to be an integer between 0 and 5, inclusive. But it can't be 6, and it can't be negative. It can't be 7. It can't be bigger than 5. So here we go. When we multiply a times b, we still have our equation for a and for b because we translated using our translation to get these two equations. They're still the same. A is still 6q1 plus 2. B is still 6q2 plus 3. So when we substitute in for a and b using our equations and multiply this out, the next step is to remember, oh, we're dividing by 6 and we're hunting for the remainder. So we ask ourselves, can we factor 6 out of what we see? And what is the remainder or the leftover? Well, each of these terms has a factor of 6 in it. So we can factor 6 out of each of these 4 terms, and there's plus 0 left over. This expression inside parentheses is like our big Q. It's our quotient. When we look at AB and divide it by 6, we have just found out AB is 6 times an integer Q. It's this big expression. But the key thing is the remainder is 0 because there is no leftover because this expression was divisible by 6. So when we translate back this equation, AB equals 6Q plus 0 is the information that we're looking for. AB mod 6 is equal to 0 because that is the remainder when we divide AB by 6. Any questions?
No.
And I gave some do laters. And you also had WebAssign where you practiced finding A mod D and A div D. The do later was just to go back to example 1 and find A mod D and A div D for each pair A and D that was given. Let's just go back and look at that. Example 1 was when we first started practicing with the QR theorem. So when A was 99 and D is 2, we divided 99 by 2. We got a quotient of 49 because that's how many copies of 2 fit into 99, plus a remainder of 1. So the quotient is 99 div 2. The remainder is 99 mod 2. So the div function gives the quotient. The mod function, which is really the more important function, gives the remainder. So when we look at A equals 37 and D equals 5, 37 div 5 is this quotient 7. 37 mod 5 is this remainder 2. And the interesting problem from example 1 was when we took a negative integer A and we think about dividing it by 5. It turns out we had to multiply 5 times negative 8, which gets all the way down to negative 40. Why did we overjump the negative 37 and go to the left of it with this negative 40? Because we know we have to come back with a positive remainder. For example, if we had used a quotient of negative 7 here instead of negative 8, we would have said negative 37 is 5 times negative 7. Well, that's only negative 35. And then our remainder would have had to be negative 2. But we can't have a negative remainder. That's why we multiplied 5 times negative 8 to get down to negative 40. So when we come back to hit negative 37, we can come back with this positive remainder 3. Does that make sense?
Yes.
So what is negative 37 mod 5? Remember, the mod is the remainder.
3.
3. Good. And what is negative 37 div 5? Remember, the
Negative 8.
div is the quotient, negative 8. Good. It's also sort of interesting to review part 4 because here our dividend A is 9 and the divisor D is 12, which is larger than 9. And when we think about it, we realize 12 doesn't fit into 9. It's too big. So 9 is equal to 0 copies of 12 plus a remainder of 9. And don't worry, 9 is not too large a remainder because the divisor is 12. So 9 is less than 12, and it's fine to have a remainder of 9. What is the largest remainder that we could obtain if we're dividing by D equals 12?
9.
Oh, let's look at our quotient remainder theorem. It says if we divide A by D, we get a quotient Q and a remainder R, where 0 is less than or equal to R is less than the divisor D. And let's just remember, when our divisor D was 2, the remainders that were possible were 0 and 1. Because 0 is less than or equal to 0, and 0 is less than 2, and 0 is less than or equal to 1, and 1 is less than 2. So 0 and 1 are the remainders when we divide by 2. When we divide it by 3, the remainders are 0, 1, and 2. The smallest remainder is always 0. The largest remainder is the integer just before the divisor. So 2 is the biggest remainder when we're dividing by 3. So if we're dividing by 11, what is the biggest, if we're dividing by 12, what is the biggest remainder that we could obtain?
11.
11. Good. So I hope that that helps you with the day 12 information. Do you feel better about it now?
Yes, thank you.
You're very welcome. I'm going to stop sharing and let someone else now ask a question. Karen, I think you were in the room right after Malala got into the room. Do you have a question?
Yes, but it wasn't a question about the homework. I wanted you to go over the proofs and the definitions from the beginning, like 4.1, 4.2, composite, primes, and perfect square for the proofs.
Okay, how about we look at quiz 3?
Okay, that works too. At the end of the office hour, are you still gonna do like a test tree review from like stuff that are gonna be on the test?
That's what we're doing now.
Okay.
That's what you're coming to me with questions about material from chapter 2. I haven't typed up the worksheet that we're going to look at on Tuesday after lecture, but I did email you a list of problems from the eBook that you can work on for proof by contraposition. And that idea of going into the eBook and looking at the review exercises at the end of each section is a way to get review. I'll show you how to do that after we look through these definitions. So let's just take a look at this quiz because you want the definitions, which surprises me because they are in the notes.
No, I have the definitions. I mean, like using the definitions in a proof, like composite.
Okay. So you'd like to see an example of a proof involving composite.
Yeah.
All right, let's see if I can make one up on the fly. Let's do an you want a universal proof because you want to have to, well, even an existential proof requires us to use the definition. Do you remember the definition of composite?
Yes.
So
Is
here, N is composite if N equals, let's say, A times B, where what do we know about A and B?
they're integers?
Good. And what else?
A is smaller than 1 and B is bigger than 1.
I think you want to say they're both larger than 1, or 1 is less than both of those. You want them both to be bigger than 1. Let's look at an example. 6 is equal to 2 times 3 is composite because 2 and 3 are integers, and 1 is less than 2, and 1 is less than 3. Does that make sense?
Yes, it does.
Okay. I'm sure that's what you meant. So let's look at another example. Prove there exists prime numbers P and Q such that P is not equal to Q and 2 to the P minus Q is composite. All right? So it's an existence proof. We're on the hunt for primes P and Q that are distinct with the property that 2 to the P minus Q is composite. So let's try some different values for P and Q. Does the red show up okay?
Mhm.
Yes.
All right, so let's try. I don't know, what would you like to try for P and Q? They have to be different from one another.
7 and 8.
Okay, stop. There are a couple of hints that I tried to give you when we first started looking at proof by example. Keep it simple, keep it small.
2.
We can try 2. We could try 3, but I don't recommend jumping to 7, and 8 isn't a prime. But okay, so we can try P equals 2 and Q equals what? They both need to be prime. Let's just use 3. Let's just use 3. These are primes, right? Let's just try that. So they're primes. We'll be able to verify it for sure. Do you agree that these are both prime?
Yes.
2 to the P minus Q is equal to 2 squared minus 3. That's 4 minus 3. That's 1. That's not going to work because it's not composite. So let's try again. What would you like to try next? You try. You give me a couple of primes, P and Q.
I would say 5.
Okay. And why don't we stick with q equals 3? And let's just see what happens. They're definitely primes. Do you agree?
Yes.
I'm just trying to keep them small, keep it simple. Okay, so 2 to the p minus q. Well, 2 to the 5th minus 3. What is 2 to the 5th? That's
Mm,
32. Minus 3. That's 29. But 29 is prime. So that's not going to work. What if we switch it around and we use p equals 3 and q equals 5? How about we try that?
mm-hmm.
All right, 2 to the p minus q is 2 cubed minus 5. That's 8 minus 5. That's 3. And that's not composite because it's prime. All right, we got to keep trying. What about p equals 3 and q equals 2? We tried p equals 2 and q equals 3. Why don't we switch them around and see if that works? 2 to the p minus q. So 2 cubed minus 2. What is that?
Six.
It's 6 because it's 8 minus 2. And that is equal to 2 times 3. So it is composite. So we have found, using our scrap work, a nice example of primes p and q that are not equal that satisfy 2 to the p minus q as composite. Let's write it up. So consider, since it's an existential statement, I like to consider instead of assume, but you can say assume p equals 3 and q equals 2, but I'm going to say consider
And do
2.
you want us to show you the scrap work?
You're going to need to do scrap work to figure out the p and the q. You might as well show it to me, even if you just do it on scrap paper.
All right.
I mean, on homework, didn't I always ask you to show scrap work?
Not necessarily. I don't know. I don't know.
Hmm. Okay. So here we go. We have to verify that P and Q are prime. That's a critical step in an existential proof. So first, we verify P equal 3 and Q equal 2 are primes. And you can say prime or primes. It doesn't matter. They're both correct. It's weird. English is weird that way. Well, notice there are two parts to the definition of prime. 3 is greater than or equal to 2, and its only positive divisors are 1 and 3. Also, 2 is greater than or equal to 2, and its only positive divisors are 1 and 2. That's what it takes to correctly verify that those are prime. And now for
Do we?
part 2,
Oh,
we
sorry.
just show this and we make sure that we address all parts of the definition of composite. All right, now 2 to the p minus q equals 2 cubed minus 2 equals 8 minus 2 equals 6. And here we go, 6 equals 2 times 3. So that's our factorization where, n is equal to a times b, where 2 and 3 are integers. You just say it. That's part 2. A and B are integers, or part 1, depending upon how you do it. And 1 is less than 2, and 1 is less than 3. We have to verify 1 is less than A, and 1 is less than B. So we have completely addressed the definition of composite. We've factored 6 into what we call a non-trivial factorization of integers. It's non-trivial because both of the factors are larger than 1, and that automatically ensures that both of the factors are less than 6. So 6 is composite. Now let me show you how you can use the ebook as a resource for extra practice. I'm going to share my screen. I'm going to go to WebAssign. I'm going to go to the ebook. And you wanted specifically something about composite. So I'm going to search the course up here in this corner. And if you're not here, like if you wind up like, in the middle, of some chapter or section, and you don't know how to get back, the way you get back is you see this menu up here. If you hit this menu, it'll give you the chapter contents of the chapter that you're in, but then you can just say table of contents. And then you can get chapter by chapter, okay, different chapter contents. But now let's do a different search. Let's search for composite. Composite. Okay. Now, chapter 4, even, odd, prime, and composite. Chapter 4. So it's in chapter 4. Let's click the first one. All right. And if you don't know what section we're in section 1. You can tell because it's example 4.1.1. Right. So here's composite. It's highlighted in blue, so it gives the definition. And notice that Epps' definition of composite is more complicated than mine because she says N is equal to R times S for integers R and S. That's the same as the definition I gave you for composite, but she has a more complicated inequality about R and S. She says 1 is less than R is less than N, and 1 is less than S is less than N. But if you think about it, if both 1 is less than R and 1 is less than S, then the other one has to be less than N. So you don't really need these double inequalities. Knowing that 1 is less than R forces S to be less than N, and knowing 1 is less than S forces R to be less than N. So that's why I trimmed down that definition and just said 1 has to be less than R and 1 has to be less than S. So here are here's some good reading, some very good reading that you can do. But now I'm going to go to the exercise set 4.1. So let's see if there's anything about composite. Here we go. Assume that R and S are particular integers. Part C, if R and S are both positive, is R squared plus 2RS plus S squared composite? That's the first proof we ever proved about composite numbers. We proved this. The answer is yes. And I'll show you where that is in the notes in just a minute. Okay, let's take a, so you can just scroll through and look at different problems. Some of them have answers. Okay. And then there'll be some questions that are outside the scope of what we covered. But there are lots of nice problems at the end of these sections. Let's go now to section 4.2. Remember, there was one section of chapter 4 that I said, if you don't ever read any section in the book except this one section. Please read section 4.2. Do you remember that?
Yes.
Yeah, it's worth reading section 4.2 because it's writing advice. So I'm going to assume that you took my reading advice and read section 4.2 on writing advice. And we're going to go to exercise set 4.2. Here are some exercises about evens and odds. They're wonderful. Here's something about perfect square, more odds, primes. Here's a theorem about composite. And it says find the mistake in the proof. So they've given a proof for a statement. This theorem is for every integer k, if k is greater than 0, then k squared plus 2k plus 1 is composite. That is actually a true statement. If k is a positive integer, then k squared plus 2k plus 1 is composite. But here's a proof that's got a mistake. The proof says for k equals 2, k is greater than 0, and then the author plugged in the 2 into k squared plus 2k plus 1 and evaluated that, and that is the integer 9. And then the author said, hey, since 9 is 3 times 3, 9 is composite. Hence, the theorem is true. What is wrong with that proof of this theorem? Does anybody know?
I think it's the 2 squared plus 2 times 2 plus 1.
That's evaluated correctly. If you do insert 2 for k, 9 is the correct value. So good to check the algebra first. But I don't think you'll ever see what's considered a poor proof given as an example for you where the problem is going to be algebra. It's something more fundamental.
I think they forgot to say that they're integers, a and b and is bigger
Yeah.
than
But
That's good. You know the definition of composite, but that isn't actually the problem.
yeah, but
If
you
the
said,
rest of the proof was okay, then you would be dead spot on, but that's not the problem. Abu, do you see what the problem is?
well, I'm thinking, you said every integer, right?
You're right.
And
You've
then,
got your finger on it.
yeah, and then you just gave, what is it, 2? I mean, anything greater than 0, but then you just gave 2, it could be any other number. You could try another number from, what you said, uh,
That's right.
for every integer, like
It's
that's
a
every.
right. The key here is this theorem is universal. It's for every integer k. It's a universal statement. We cannot prove a universal statement by example, can we? So actually, I'm going to stop sharing and I'm going to prove this for you. We'll call this example 2. Is it example 2 or is it example 3? It's example 3 theorem. If k is an integer and k is greater than 0, then k squared plus 2k plus 1 is composite. We cannot prove this by example. We have to use variables, definitions, and algebra. And also things we may assume. So here's our hypothesis. We're going to prove this directly. We're going to assume the hypothesis, and then we wish to show that this conclusion follows. Do you agree?
Yes.
So proof. Assume k is an integer and k is greater than 0. There's another way to say that. And I am going to show you the class notes where we proved the other statement we saw. We could just say assume K is in Z plus. That's what it means to be in Z plus. It means K is a positive integer. You could say the hypothesis either way. Now let's take a look at this expression. K squared plus 2K plus 1. Well, you have to be able to factor. It's K plus 1 times K plus 1. And because K is greater than 0, K plus 1 is greater than 1. Also, K plus 1 is an integer because sums of integers are integers. So K squared plus 2K plus 1 is composite. We've addressed all the parts of the definition of composite. We've got K squared plus 2K plus 1 looking like A times B. Well, they happen to be the same number, so it makes it a little easier. Here, we verified that A and B, because they're the same thing, they're both K plus 1, are both greater than 1. And we've also verified that both A and B are integers. So if you're having difficulty with the definition of composite when it is a universal statement, it might be because it's going to require factoring, and that might be something that you're not completely comfortable with. I want to share my screen one more time, and let's go back to our reading page and find the day of class notes where we first started chapter 4, and it's right here, day 9. It's where we got all these definitions. An integer n greater than or equal to 2 is composite if there exist integers a and b such that n equals a times b and 1 is less than a and 1 is less than b. And these parts don't have to appear in this order in your proof. And in fact, we talked about proving existential statements, but then we dug into proving universal statements. The first thing we learned is you want to write your universal statement as an if-then statement so you can get your eyes on the hypothesis and the conclusion, remember? And we identified the hypothesis, which is what we will assume because this is for direct proof. Notice I said direct proof method there. That did not mean much to you then, but now that we have the proof by contrapositive, you know there is a different method. So we did a nice, easy little proof about the sum of two even integers is even. Remember that? Remember that first proof for a universal statement? And now that looks easy, doesn't it? Because we assumed A and B are even integers, you know to assume the hypothesis, right? And we applied the definitions, we got our proof money, we used our proof money, we factored out a 2, and we were careful to talk about M being an integer because K and J are integers. Their sum is an integer. That all looks easy now. But in example 5, I wanted to teach you about disproving statements. Remember, to disprove a false statement, we prove its negation. So I gave a false existential statement. There exists a positive integer n such that n squared plus 3n plus 2 is prime. That's false. The negation is for all positive integers n squared plus 3n plus 2 is not prime. And in fact, here it's actually going to be composite. So if n is a positive integer, then n squared plus 3n plus 2 is not prime. But as we work through the proof, we find out the reason it's not prime isn't because it's too small or negative or something. It's not prime because we can factor it. So we assume n is a positive integer. Remember, that means n is greater than 0. It's the same hypothesis that we had with this proof we just did. And we want to show n squared plus 3n plus 2 is not prime. So we factor it into two factors, n plus 2 times n plus 1. The first thing I argued here with you was that, hey, a and b are integers because n is an integer and sums of integers are integers. The next thing we have to do is argue that both a and b are bigger than 1. But n is bigger than or equal to 1 because it's positive. So a, which is n plus 2, is bigger than or equal to 1 plus 2 because the smallest n can be is 1. Well, that's 3, and that's bigger than 1. See, the smallest a can be is 3, and that's bigger than 1. The smallest b can be is 2 because it's n plus 1, and n has to be at least 1. So both a and b are bigger than 1. So finally, I just verified that that expression, n squared plus 3n plus 2, is bigger than or equal to 2. But you could glean that. It's the product of two factors that are at least as big as 3 and 2. So that would be another way to say, hey, n squared plus 3n plus 2 is big enough. It's at least 2. And so we have shown n squared plus 3n plus 2 is a times b for integers a and b with one less than a and one less than b. So it's composite. So I encourage you to go back and look at that now with fresh eyes. Does that help, Karen? Karen, you were the one that asked this question.
Yes, I did. So I understand everything you just said.
That's great. And there are some do laters here from that.
Yeah,
So,
there's the book too, the
yeah,
example
and you've got the
4.2.
book. Now,
Mm-hmm.
folks, I'm going to take a question. So, Alpha, you came in, and Abu, you came in. Alpha, do you have a specific question that you would like to ask tonight?
Eh, I mean, we've still got time. It's 7:03.
I know, but I'm willing to go a little bit longer tonight, just to at least give you and Abu a chance to ask at least one question, if you have
Okay.
one. Or we could go over the quiz solutions, but I'm going to post these quiz solutions, and you could have looked these up, you know, anyway. So I don't want to waste time. Is there a topic or something that's nagging at you?
I think I'm good for now. Like anything else, I'll check the notes or read the textbook.
Okay. Abu,
But
did
yeah,
you have
thank you.
You're very welcome. Abu, did you have a specific question or definition or something that's bothering you that you need help with?
No, Professor. I just wanted to, like sit in. Um, I just
Okay,
want,
so
yeah.
okay. So here's some suggestions.
Okay.
Review all class notes, special homework, and of course, quiz 3. So you've gotten feedback and you'll get your special homework back. I've already graded section 9 of the special homework that you turned in this week. So I'll have that for you Tuesday. Do all due later problems. Do use exercises at the end of sections 4-1, 4-2, 4-3, 4-4, 4-5, 4-7, and then I'll put a star by 4-8 because and this one because proof by contradiction we haven't done yet. We're going to do that Tuesday. But you can also view office hour videos because we've had a lot of them that maybe you didn't ever view. and view the special topic videos. Because this can give you a jump start on proof by contradiction. And I sent an announcement with a list of specific questions to help you with proof by contrapositive. I went through and curated some particular problems that should help you from section 4.7. Okay? Exercises listed in our March 29th announcement for proof by contrapositive. And of course, I say I should put definitions at the top, review, definitions, class notes, special homework. You can also review WebAssign because you can go back in and look at those problems, right? In quiz 3 and do all the due later problems. And then these are the sections that will be covered on the test. Office hour videos. And listen, you don't have to watch the whole video. If you go to YouTube, my YouTube channel at Liz Good 2766, if you go to my YouTube channel and look at the description of the videos, I tell what we covered in that video. So you don't have to watch a whole video and not know what you're going to see. Read the description. Read the descriptions. And that's not in Panopto, but that's in the YouTube. The videos are posted in 2 places. Okay. And it might be better if you go to the YouTube because the descriptions are there in the YouTube. So that's a really good way to start getting ready. I know what you wanted me to do was just give you a list of questions that you could work on. But that is not the best way for you to learn this material. The best way for you to review is to go through your notes and make lists of problems yourself that you didn't understand or a problem that you didn't do well on in your special homework. Make a list of those and bring those in Tuesday. And then when we're workshopping, you can ask or you can try to rewrite your proofs. And I've always said you can email me PDFs and I'll look at them. So there was all of spring break to do that, but nobody took me up on it, but that's okay. It was break. All right, we are going to have an office hour tomorrow night, the usual time. And then we can even probably have, well, we'll have an office hour Wednesday night. I know some of you have a class on Monday and Wednesday at that time, but the videos will go up. Okay,
Maybe able to tune in for Wednesday nights if I'm
I
not
hope
too
so.
busy. Yeah.
Okay,
Okay, thank you so much, Mel.
you're
Yeah,
welcome.
thank you,
Thanks for,
Professor.
Thank you, Dr. Good.
thank you for coming.
Thanks.
Jessica, oh, wait a minute. Jessica, you're here. I didn't see you. Did you have a question, Jessica? Gosh, I'm so sorry.
Nope, all my questions were answered.
Okay. All right, great. Thanks.
Thank you.
Good night.
Good night.